Sup guys, XX Sonica XX, FRQ 5, number 4. Let's go. The graph on the right here, shows the potential energy diagram of a block oscillating on a spring. So the block is moving back and forth attached to the spring, where X represents the length of the spring. Part A. What is the equilibrium length of the spring? How do you know that is the equilibrium length? So we know that potential energy of the spring equals 1/2 spring constant x squared. Now x stands for the distance the spring is either stretched or compressed. If it is neither stretched nor compressed, then it is at equilibrium. Basically when x equals 0. So we'll plug in x as 0, 1/2 k, 0 squared, which means everything cancels out to 0, and that will be the potential energy when the spring is at equilibrium. Now, back to the graph. The only time the potential energy is equal to 0 is at 20 centimeters, right here. So that is our answer, 20 centimeters. Part B. If the block's turning points are 14 centimeters and 26 centimeters, draw a line that indicates the total energy. Okay, so Part A. Part B, total energy, I'll call it ME for mechanical energy, is equal to the sum of potential energy plus kinetic energy. Now, at the turning points, basically, the block, I'll use an eraser as an example, turns around. And at that turning point, right before it turns around, the eraser's velocity is 0. So when the velocity is 0, then KE is 0. So at 14 centimeters and 26 centimeters, KE is 0, and potential energy is equal to the total energy at that point. Now, since energy is conserved, mechanical energy is always the same. So we can say that at 14 centimeters, potential energy is equal to the mechanical energy. So 14 centimeters here, 26 centimeters here, that's where the potential energy is. So we can draw a line that connects those two. And that is the line for total energy. Okay, part C. On the same graph, in part B, draw the kinetic energy KE graph. Must be accurate. Okay, so as I said before, the block stops moving at 14 and 26. So KE is 0 at 14 centimeters and 26 centimeters. And because PE is 0 at 20 centimeters, kinetic energy is equal to the total energy because, let's see. Same thing as before, ME equals PE plus KE. This time, if potential energy equals 0, ME equals KE. Okay, so kinetic energy is up here at 20 centimeters, matching the ME. So we just have to draw a line that connects all 3 points. That looks pretty good. Must be accurate? Must be pretty accurate, huh? Okay, part D. Calculate the spring constant K. Okay, get it? Okay, ha ha ha. So we have to find an X that is not 0. Otherwise, we can't find K because it'll be pretty much anything. So we'll use 14 centimeters because the total energy will be around 6, and the PE 6 joules, and the PE will be equal to the total energy at 14 centimeters. So we'll set up PE spring equals 1/2 kx squared. Now, if the spring is at equilibrium at 20 centimeters and we compress it to 14 centimeters, that means it has compressed 6 centimeters or 0.06 meters. And that is our X. It compresses 0.06 meters. So P spring, as we said, is 6 equals 1/2 K 0.06 squared. 6 equals 1/2 K 0.06 squared is 0.0036. Multiply 1/2 and that together, 0.0018k. And we divide that on both sides and we get k equals 3,333.33 newtons over meters. That is our spring constant K. Okay. Part E. Determine the block's maximum kinetic energy. Now, I pretty much demonstrated that in part C, that ME equals KE at 20 centimeters because potential energy is 0 at that point. And as you look in this graph, that is the maximum of this curve. So therefore, the maximum kinetic energy can be is 6 joules, the total kinetic energy. Part F. What is the block's kinetic energy at 16 centimeters? Okay. So PE spring. First, let's write the overall equation. ME equals KE plus PE. If we isolate for kinetic energy, we get kinetic energy equals mechanical energy minus potential energy. Now, we know mechanical energy will always be 6. But how about potential energy? We can use the PE spring formula in this case. So at 16 centimeters, it has compressed 4 centimeters or 0.04 meters. And as we found out in part D, K is 3333.33 over all over 1/2 equals our PE spring at that point. Calculate that, and we'll get 2.67 approximately joules. So we can plop that back in. 2.67. 6 minus 2.67 gives us our KE, which is 3.33 joules. That is a lot of 3's. And lastly, part G. Part G asks, what will be the turning points if the block's total energy is doubled? So, as we approximated, our mechanical energy would now be 12 joules. And at the turning point, there is no KE and just PE, which means PE will also be 12 joules at the turning points. But we have to find that out. What's the turning points? PE spring equals 1/2 kx squared. We have to find x. So 12 equals 1/2, bunch of 3's, x squared. Divide that by 2, 1.666.67 or 1,666.67 x squared. Divide that, and we get 0.0072 equals x squared. Square root both sides, and we get x equals 0.085 meters. And to convert it to centimeters, we multiply by 100 to get 8.5 centimeters stretched / compressed. So, if we want to reach the new turning points, we have to stretch or compress 8.5 centimeters starting from the equilibrium. So if we compress it, we will subtract 20 by 8.5 to get 11.5 centimeters, the first position in which there's a turning point. And to find the other one, we add 8.5 centimeters to get 28.5 centimeters. So these two are our new turning points when our mechanical energy has been doubled from 6 to 12. And that is all the parts for question 4. Stay tuned for our last part, question 5. See you next time. Peace.